Hello community. After two fantastic videos how LLM can fail, I have made a third video about in-context learning at below 1K token length. And ICL, one-shot prompt. But the result of the third video are just crazy. The variance and the performance is extreme. So in-context learning here, it is very easy. You have a passage of text. You say, hey, this is the task, and I would like you answer in this. So you teach the LLM what answer, what form of answer you would like to have. This is it. Can be complex, can be really easy. So let's take a Llama 2 7B model and do a just simple one-shot in-context learning. Now, interestingly, we have a passage and we have an answer, and we give here one example to the LLM. Now, the text is not important. Let me show you this. We have here simple one-shot ICL, and we have here a task accuracy of a Llama 2 7B model of 0.03 or 3%. Great. Now, if we modify here the separator in this ICL structure in the prompt format, we get a performance above 50%. If we continue the modification and we insert here a different connector, we get a performance that is maybe above 60%. If we go with the original formatting, how the Llama 2 has been pre-trained, we get now here in blue, you see here, passage, text, answer, text. We get now a performance here, let's say close to 70%. And now comes the interesting part. If we further optimize here the format, not the content, just the format. Look, now we do not have here /n, \n for the next line, but we have here this string, and it is not dependent on the text. We get a performance that is above 70%. And then if we just go here modifying the separator and the spacing compared to our very first try, if we use this structure of the prompt, we get a performance over 80%. The text always stays the same. We just modify single characters, single formatting options, single separator, single connector, and single spacing. How is this possible? What it shows us that we have a minimum and a maximum performance across a set of semantically equivalent prompt formats. And this is really from 3% to over 80%. And this explains my extreme problem with my third video on ICL. Now, some really intelligent people notice this. And they say, hey, let's define all valid prompt formats, all theoretically possible prompt formats, and let's test them. So they define here a pseudo-grammar for a pseudo-prompt format language. You can see them here. And then they separate here the specific set of separators. And as you can see, you have here a new line, then you have here dashes, then you have separator here printed out. And all different here, S2, for example, we have no space, we have a single space, we have a double space, we have a tab, and then we have here a set of connectors. And they have now constructed here with this grammar a kind of a language where they can say for one prompt, I can give you up to 500 variations on the different separators, on the different connectors, on if we have a bullet list inside, if we have any kind of formatting. And they constructed this. And they said, hey, why not two prompts equivalent? And they had here a mathematical definition. And they refer here to proceeding of the Association of Computational Linguistics in December 2022. I have not been aware at all. I missed on this, I have to tell you. We have UC Berkeley, we have Stanford University, we have Johns Hopkins University. Please have a look at this. And there was something I remember. In beginning of 2021, we had this by the Stanford AI Lab, when they were talking about ResNet features. This is about visual object recognition. You will not have heard about this if you are younger. Never mind. But they said, hey, what we find, and I showed you this in a very old video of mine, it was about X-ray. It was medicine and AI. And they had a lot of X-ray, chest X-rays. And of course, this was the training set for an AI to learn. Now, as it turned out, the machine did not learn to analyze the complete visual information here of this X-ray image, but decided to base its criteria for decision-making on here a very tiny handwritten text where the assistant, the human medical assistant, for themselves made here a cross or a X or whatever, a very tiny symbol to indicate if this is an image, positive or negative. And this, they found out, served as an indicator regarding the decision-making by the AI, not the content of the image. And I did not make the logical connection that this is also happening here in the language modeling, until I found this publication. Congratulations to those people, University of Washington, Allen Institute for Artificial Intelligence, and UC Berkeley. Because they analyzed the sensitivity of widely used open source LLM to a class, to a very specific class of features that should not influence a prompt interpretation, but it does massively. And these are visibly or not visible formatting choices. So whenever I copy a piece of text and I put it in a prompt to my GPT-4 system or a Mistral system, there are visible and invisible formatting choices, like an empty space, like, I don't know, curly brackets, a colon, a semicolon, a full stop, followed by a different separator. And I never paid attention to these particular features because I assumed as a human, hey, an empty space, what is the semantic relevance for a human? Almost nothing. But boy, it turned out for a machine it is completely different. So let's see the result of this study. Again, they used here the inside and they looked here exactly here at the different spaces, at the different separators between text and different options, about the formatting and. Let's have a look at the results. What is interesting, they did this for different models and it turned out we have a prompt format sensitivity for different model. You can see it here. We have here a Llama 70B model. And you have two prompt formatting options. The first option is here this. Second prompt formatting option is this. The performance of the first option is 83% in the accuracy. The performance of the second option is 7%. And they did this here for, I think, several hundred tasks and several different hundred of different prompt formatting alteration, as you can see here. Sometimes it's really tiny. You see here, comment, answer, 58%, 51%. But sometimes, especially if I use in-context learning to tell my ICL, look, this is the kind of information I give you, and I wanted you answer in a very particular way. And if you have a context, a question, and an option how you can answer, mathematics, physics, chemistry answer, there can be massive differences just how I format the prompt, independent of the content of the prompt and completely independent of the semantic content. You see here, this has a 38 performance. This structure has only an 11% performance. And you know what? It is here depending on the LLM, how the LLM has been pre-trained, how it has been fine-tuned, and how it has been instruction-tuned. And I was not aware of this at all. Look at this data here from this study. They choose here GPT 3.5, our old Chat GPT. And the idea was, okay, but Chat GPT, let's formulate it in a friendly way that tried to agree to copy the internet here. So everything, but this huge model must be able to overcome this limitation of a single character in a prompt format. And as it turned out, well, no, ChatGPT has exactly the same sensitivity. Maybe a touch less, but look at this. For this option, 24%. For this option, 9%. If you go with this option here with 98%, and for this format of your prompt, 80%, you say, okay, at least 80%, if not 98%. But there are really some grave outliers, and this can crush your model performance completely. So they did here a systematic study with this grammar with each specific LLM, and they came to conclusion. And yeah, one of my viewers asked, hey, there wrote a comment, hey, did you notice, asking me, that you did not just ask for the information in my last video here, but you ask for a task to be performed in the middle of your sequence. Yes, I constructed this test. Yes, I know that I put in there an instruction. And you know, we call this instruction induction task. And there's a special reason why I did it and redo it is, so it refers to a specific type of task designed to evaluate and improve the capabilities of our LLM, in particular in understanding and following more complex instruction. And this is an important task for different reasons. Complexity. We want to generate here a unique and valid strings given a set of instruction. So this is about, is the model able to perform some logical steps? And then instruction can be really nuanced and really complex. And we want to see, does the model really understand also the detail? And it goes absolutely beyond simply providing information, and the LLM has to extract information. But I want the LLM to perform also a task. So we have task-oriented scenarios, and this is why I chose this very particular format in my last video. However, this gives us an insight into optimization, how we train our LLMs and how we achieve here an overall better functionality. And of course, it's about real-world application. Because standardized benchmarks, they are great because they enable us to compare different models. But you know what? Standardized benchmarks just look at one very particular configuration of data, and then you test all the models on this. And this is great. But you know, the more modern models, they know about the test algorithms. And they understand exactly how they are evaluated, on what structure they are evaluated. And of course, they want to improve. So they think about clever ways to improve the general performance of their model. So the real-world applications are more and more missing in this. We go to standardized formats, which are great by themselves. But maybe we are missing out here in the real-world application on something. And I want to show you this. This is one of the results. And I think this is so beautiful. And this is now exactly figure 18 of this publication on instruction induction. So what I did in my last video on the accuracy across different models. And now we only not have different models like the Llama 2 7B and the Llama 2 13B and the Falcon 7B and the Falcon 7B Instruct, but we also have different N-shot learning examples. So if we go here with a one-shot prompt, what we see? We have 0 here, and then we have the perfect accuracy with 1. So either you go from 0 to 1 or from 0 to 100%, depends on you. This shows you here the accuracy over the prompt formatting that you can choose. This is a box plot, and I'll explain exactly how you can read this at the end of this video. But I just want to show you here, if you don't know about here, the 5 particular indicators here of a box plot. Just here, look here at the solid box. You can see, without here even the whiskers, you are somewhere at 10% and you go up to 80%. So it is the same Llama 2 model with 7B. You have the same semantic content in your one-shot example. But the performance of the model is either 10% accuracy or 80% accuracy, just depending on the prompt formatting. And you can go with other models. And if you have here a Falcon 7B, you have here outliers that go all across the spectrum. So this is something that they found that I have not been aware, but now I have a better understanding. Yeah, that's funny. Just to show you here one of the results, and this is a specific task, and they have here the prompt format 1. So here we provide also a one-shot example, a passage here, curly brackets, an answer, curly brackets, and then prompt format 2 is now a tiny bit different. Passage, curly bracket, answer, curly bracket. Now guess the performance difference for an identical model or the identical text in the curly brackets, just given this prompt formatting for a one-shot example. What would you guess? The difference is between 4% to 82%. So the model is the same, the model size is the same, the text is the same, the semantic information is the same, just the prompt format. If there is an empty space before the curly bracket or not, gives you a difference of 78 percentage points in the performance, in the overall performance of the LLM. So the researchers found here this beautiful sentence: small prompt variation often yield large performance differences in the LLMs. And this is something I have not been aware of. You know what else is bugging me? I thought if I would go with the original formatting of a Llama 2 7B, when it has been formatted, when it has been created, pre-trained, fine-tuned, or whatever, I thought that this blue box would have the best performance. No, this structure here, this prompt formatting configuration has a 10% better improvement. How is this possible? Why? I don't know yet, but it is fascinating. Now, the authors here, the universities here, had similar thoughts, and they developed here now this grammar methodology to simply test all possible configuration. Run through this hundreds and 10,000 times to find here a solution. Now let me tell you here the results of their endeavor. So they introduced here a new tool, format spread. This is an algorithm that estimates here the performance spread, as I showed you, from some single percentage to 80% across prompt formatting choices. And what they found is that the spread, the variation, is large, regardless of the model choice. If you go with a 7B model or if you go with a ChatGPT model, regardless of model choice, it is there. If you increase the model size just by the trainable parameter, if you change the number of the few-shot examples from 1 to 5, or if you use instruction tuning, yes or not, it is there. They used here a particular set of 40,000 evaluation and a complete set of 320 different prompt formats to evaluate here their findings. And they say, hey, even with a 5-shot Llama 2 70B free trainable parameter model, it still shows a high spread. 25% of the tasks have a spread of 0.3 and a maximum of 84%. So it is across the models, across the size, across the number of few-shot ICLs, across instruction tuning, yes or not. And they say, you know what? Ignoring here the variance that we have across these different prompt formats that you can input here your query, this may have a negative effect on the user experience. So what does it mean for me? What have I learned from this exercise of performing here 2.5 videos? Now I understand that I missed out here on the prompt format optimization. I understand now that I need to develop here a prompt format optimization tool that is specifically tailored here for each of my specific pre-trained models that I use. I use GPT-4, for example, and 3 other open source models. I have to optimize also here when I construct here a fine-tuning scheme, and in particular here an instruction tuning data set with my data. I need to pay attention here to each and every single separator, connector, and I have not been aware of the importance of the prompt formatting optimization as a core component to increase the performance of my system. So having found here an optimized format, I simply will have to refine-tune here my LLMs. I take here a pre-trained LLM and then I refine-tune it on 20,000, 100,000 scientific articles about theoretical physics, about chemistry, about whatever. So I have to redo here simply my fine-tuning. I hope for an additional boost in performance of my model. And in general, I have here to establish a prompt optimization strategy that goes for whenever I use a prompt in whatever system for whatever model, for whatever model size, regardless if it's in context learning with a 1-shot or 5-shot, I provide information to proprietary LLMs. So in context learning, everything that is connected with chain of thought, I think there's a lot of performance to gain, and I have to customize this simply for my LLMs. I also looked here at RAG system, the retrieval augmented generation, because they used here very specific prompt templates. And I had high hopes that those open source RAG systems were already optimized here for particular models. They would not use here template structures in an intermix for models, but they would have a prompt format structure in their template that is absolutely specifically fine-tuned for specific LLMs, either pre-trained or fine-tuned or instruction-tuned. And I had a look at 3 different open source RAG systems. And let me formulate it in this way. I think there is, to uncover any latent format optimization, yes, there's a real open space where your RAG system can be significantly improved with taking care about prompt format optimization. I have no access to proprietary RAG system where you pay thousands of dollars per month for this. I cannot evaluate this. I have no access and I don't want to pay for them, honestly. So if you are, or you build your own RAG system and you were not aware here of the prompt format optimization, what it can bring to your system, maybe you decide that you might have a look at this system. Yeah, and in total, I think I have to strive to maintain coherence in my prompt formatting across all my stages. So including fine-tuning, including instruction tuning, including here all my query formulation in whatever system I address. I understand that my prompt cannot be the same for 2 different systems or for one system that has a different fine-tuning. So I think there's a lot of work I think that I will have to experience, that I will have to test out. I will get my ideas how I can do this and find an optimization for my data sets and for my LLMs that I use. So, and if you think about a mixture of expert system, or you think about LLMs that have been merged together, I think we have not even touched upon how we optimize here our prompt format. But of course, we do not end a YouTube video here with something about me. It is all about my audience. It is about my younger audience, for Ben, for example. So here a short explanation. What is a box plot? What is a box and whisker plot in detail? What is the statistical data that are presented in these 5 parameters? Minimum, first quartile, median, third quartile, and the maximum values. What is exactly here this whisker indication? What are outliers? And I give you here, no, not E. ChatGPT-4 gives you here an explanation And I ask here ChatGPT-4 for a particular example. So let's say we have those values in our set of values that we want to analyze statistically with a box plot. And here, ChatGPT-4 goes through all the different things, shows you how to calculate each and every value, and then how your box plot would look like, and gives you the exact value of the plot. So if you're not familiar with this, this is a special service for my younger viewer. It would be great to see you in my next video.